Greetings again, this is Steve Miller. Welcome to the fifth of the regression lectures for the LACOL Summer Data Science class. So what I want to do in this lecture is talk a little bit about the theory. So how can we prove our conjectured formula for the best fit number of tanks, the best guess for the number of tanks produced as a function of the largest serial number observed and the number of tanks observed. So this is all advanced supplemental material. If you are interested, I encourage you to listen or email me for a write-up. If not, missing this is not going to affect your understanding of the rest of the unit. Okay, so some mathematical preliminaries. So what's nice about this is even if you do not care too much about the theoretical derivation, this is a way to just review some good math. So the first is the function n factorial, the factorial function. So it's the number of ways to order n objects when order matters. So there's a difference between being president, vice president, secretary, and so on. So there's n choices for the first person to choose. And now we have n-1 people for the second slot, and so on and so on and so on. We defined 0 factorial to be 1. We said there's one way to do nothing. The next is n choose k. It's the number of ways to choose k items from n items when order doesn't matter. So think of it as we have n people and we're choosing k to serve as congressmen. And all congressmen are equal. It's unlike the executive branch where you have different offices. And it turns out it's just n factorial over k factorial, n minus k factorial. And the last is the binomial theorem. So if you have x plus y and you raise it to the nth power, it's the sum of n choose k, x to the k, y to the n minus k. So you may have seen these numbers in Pascal's triangle. In fact, we have the beautiful relationship n plus 1 choose k is n choose k plus n choose k minus 1. So for instance, if we expand things out, we get 1, and then x plus y to the first is going to be 1x plus 1y. X plus y squared is going to be 1x squared plus 2xy plus y squared. X plus y cubed would be 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed, and so on. And so Pascal's triangle, n plus 1 choose k is n choose k plus n choose k minus 1. So each number is the sum of the one to the left and the right. So 6 is 3 plus 3. 5 is 1 plus 4. 15 is 10 plus 5. And if you want over here, this 1 is going to be 1 plus, if you want to consider it a 0, you can consider it a 0 that way. So how can we prove Pascal's identity? There's a lot of different ways. So imagine we have n Red Sox fans and we have 1 Yankee fan. So a great way to prove combinatorial identities is to tell a story. So what is n plus 1 choose k is? Well, we have n plus 1 people, and I want to choose k people from that. Well, by definition, that's n plus 1 choose k. And now I can break this up as to whether or not I've chosen the Yankee fan or I haven't. If I haven't chosen it, if I'm in the fortunate situation when I only have Red Sox fans, it's going to be 1 choose 0. I have a Yankee fan, I choose not to take them. And now to get k people in total, I have to choose k Red Sox fans, so it'll be n choose k. Or I could choose the Yankee fan, 1 choose 1, and now of the n Red Sox fans, I can only choose k minus 1 because I want to have a group of size k when I'm done. Since 1 choose 0 is 1 and 1 choose 1 is 1, this is going to just be the claimed formula above. So this is a way to prove Pascal's identity by telling the story. Right? And so again, we can just see all of those relationships again and again. Now, it's worth remarking that Pascal's triangle has a lot of interesting properties. So what we're doing over here is, rather than writing it like this, I'm going to rotate it, and I'm going to put the vertex down here and expand it out like that. And what I'm going to do is, if it's an odd number, I'm going to put a dot, and if it's an even number, I'm going to remove it. And what you can notice is that there's a lot of interesting patterns between how the dots come. Now, if I add more and more rows, I eventually run out of room on the screen. So what I'm always going to do is I'm always going to adjust my code so that I always show it inside the same box. And as I take more and more, this is taking very few rows, even more rows, you notice that there's a fractal behavior. So a couple of years ago, I recorded a little video on this. I will just quickly play that right now. And you can see what happens as you add more and more rows. And I'm adjusting it, as I remarked, so that you always have it fixed in the same window size. So it's like we're zooming out, and you're seeing more and more of the structure. There's a wonderful fractal structure. And the reason I just want to remark about this, even though this is not really relevant too much to what we're doing, is that there's a lot of patterns. There's a lot of things going on that you may not immediately notice. So if you're looking at just one thing, don't be blinded to some other things that might be lurking nearby. All right. So returning to the main lecture, there is another relationship we need for Pascal's triangle, and that's the sum of m choose k, n goes from k to n, is n plus 1 choose k plus 1. So for example, this is going to be k equals 0, this will be k equals 1. So if we take k equals 1, and let's take n equals 5. So we have to sum 1 plus 2 plus 3 plus 4 plus 5, that's 15, and that is the number over here. Similarly, if we take k equals 0, 1, 2, 3, if we take k equals 3, 1 plus 4 plus 10, that's 15. So there's a nice way to prove this. If you're familiar with induction, we can prove this on n. So we'll keep k fixed. The base case when n equals k, well, we only have one term here. We have n choose n, because k equals n, is the same as n plus 1 choose n plus 1, because k equals n. So we get 1 equals 1. So the base case is established. And then for the inductive step, we assume we know that the sum of from k to n is equal to n plus 1 choose k plus 1. And then we just add the next term, and then we use Pascal's identity. And so this follows immediately from Pascal's identity. So now we can get to the point where we can get into the real model for the GermanTank problem. So let's let m be a random variable for the maximum serial number observed, and let little m be the value. So there's zero probability that we're going to observe a value smaller than k, because the tanks are labeled sequentially, and there's a zero probability that we'll observe something larger than n. And so the probability is only non-zero for m between k and n, and it's given by the following. And there's a couple of ways to prove this. One way to prove it is, imagine the largest serial number is little m. Then we have to have k tanks chosen overall. The number of ways to choose k tanks from n is n choose k. If the largest one has to be m, then we have to choose k minus 1 tanks from the first m minus 1. And that gives you this ratio. This ratio is calculating it another way. M choose k is how many ways we can choose k tanks from n, where the largest is at most m. It doesn't have to be m, it's at most m. And this would be the number of ways we can choose k tanks where the largest is at most m minus 1. So if we subtract those two counts, all that will be left will be the ones where the largest is exactly m. And so now by the definition of the expected value, so if you've seen this in probability, the expected value of m is m times the probability that our random variable takes on the value m. So what you do is you take each possible value and you weight it by how often it occurs. So if you've ever taken any class where not all grade parts are weighted equally, that's exactly what you do to calculate your final grade. You weight them. So maybe the final counts 40%, so you would multiply your score for the final by 0.4. Maybe the midterm counts 30%, so you multiply the midterm score by 0.3, et cetera, et cetera, et cetera. So we know what the probability that we take on a value of m is. M has to range from k to n. It's m minus 1 choose k minus 1 divided by n choose k. And now we just do a bunch of algebra. So I will just say a few words about the algebra. The only reason it works out at the end is these wonderful Pascal identities. And so we expand what the binomial coefficients are. We arrange things, we do some cancellations. We have this sum over here, and now we use our identity to replace that sum with something that's closed. And that's where the miracle is, that we have that identity. Well, now that we have that, we expand that out in terms of factorials. We do some cancellations, and we get a beautiful simple formula at the end of the day, the expected value of m. It's just going to be kn plus 1 divided by k plus 1. So we can now solve for n in terms of m and k. So n is going to be the expected value of m times 1 plus 1 over k times, minus 1. So now we just substitute in for big M. We would substitute in the observed largest serial number, and this will give us our prediction for what that tank should be. So the number of tanks produced, we will predict the best fit value for that is going to be the observed value of M times 1 plus 1 minus k minus 1. And again, just putting in this chart, the more time to look at it, the better. just the wonderful job this theory does. So because we were good theoreticians, we were able to prove this. But what if we weren't able to prove it? What if we didn't see how to do this? We still want to be able to predict the number of tanks, but what if we didn't see these algebraic simplifications? What if we didn't see that Pascal identity? What could we do? And that's where statistics comes into play. And we'll talk about that in the last lecture. I want to just very quickly go through the slides of what to do if you have an unknown initial value. So I'm not going to really say anything. I'm just going to slowly go through and say that you can also conjecture a relationship. You can try extreme cases. You can do a similar argument to figure out what the probability should be. And again, if you want the details, I urge you to just email me and I will send you a copy of the paper. And then you just have to go through the algebra. So just list down what all the quantities are, and you start doing the algebra. And unfortunately, the algebra becomes a little bit more involved, which is not surprising because now we don't know the lowest value. We don't know things go from 1. So we have to work in some sense on both ends. But eventually, after doing a lot of work and even more work, we finally get to the formula at the end of the day. And so I will just leave by putting a few references on there if you want to read more about this problem. It's an absolutely tremendous problem.